All right, we're working on some optimization problems, working with composite functions here. For the first example, we're determining the absolute maximum value of this quartic function. Actually, it's not a quartic, it's going to be degree 8 over this interval. So I do have a fixed interval, but what I need to find within that interval are any critical numbers. And to get those critical numbers, we know we need to take the derivative and set it equal to 0. So that would be my first step with this question. So we're going to find y prime here. And I'm going to need that chain rule. The 4 comes down in front, and we're left with x squared minus 3x to the exponent of 3 now, times the derivative of what's inside, which would be a 2x minus 3. Now to get our critical numbers, we're going to let y prime equal 0, let the derivative equal 0, and we end up with this happening. And this is really nice because it's already in our factored form. So for that expression to equal 0, the only way it can equal 0 is if one of the factors is equal to 0. So that gives us x squared minus 3x all cubed equaling 0, or we would have 2x minus 3 equals 0. And then we're going to solve these for our x. Now, within this, I'm going to first of all take the cube root of both sides. So cube root this one, cube root this side. The cube root of 0 is 0, and then that just undoes what we have for our cube. It undoes the exponent 3. All right, so now what we can do is we can common factor x out of that expression, and that either gives us x equals 0 or x equals 3. So we've got two possible critical numbers, and a third is going to come from this piece, 2x equals 3, x equals 3 halves, or 1.5. Now, within our interval, we've got an endpoint at -3, and our other endpoint is at +1. In terms of the critical numbers that we have found, this is not in the interval. Not. Oh dear, that didn't come out very well. Let me try that again. Not in interval. And likewise, this is not in the interval either. Okay, so either of those are not in the interval. So the only one we need to worry about is x equals 0 here. So in terms of a fixed interval, at this point, all we need to do is evaluate the actual value of the y, the actual function's value, at those particular values. So when, oops, wrong tool, hang on. There we go. We're going to try when x equals 0. So if x equals 0, our y is going to equal 0 squared minus 3 times 0, all to the exponent of 4, and that's just going to equal 0. So its value is 0, so right now we have a maximum of 0 within that interval, except now we also need to check the endpoints of that interval. So let's say if x is equal to -3, our y value, our y will equal -3 squared minus 3 times -3 all to the exponent of 4, which will be 9, and then add 9, which would be 18, and then 18 to the exponent of 4. We'll figure out on the calculator, and I believe I got 104,976. So that value is definitely bigger than 0. The last one we need to also check is the other endpoint. So if x is equal to 1, if x is equal to 1, our y value will equal 1 squared minus 3 times 1, all to the exponent 4. That's going to be 1 minus 3, which is -2. -2 to the exponent 4 will be +16. So overall, our absolute maximum on this interval would be 104,976 when x equals -3. So hopefully that makes sense. Everything, we've done these questions before. Everything's still similar to what we've done. The only difference is we're working with these composite functions now. All right, our next example is find the closest point. Oops, that didn't happen the way I wanted to. Find the closest point to 0, -1 that is on this curve of f of x equals 1/3 x squared minus 5. All right, there are many different ways you can do this question, but I'm just going to put this in terms of the calculus context here. We want to find the closest point, or the point, if we were to pick a point that's on this curve, which is a parabola, any point on that curve would be x comma 1/3 x squared minus 5. That would be any point on that particular curve. I want to minimize the distance between any point on the curve and the point 0, -1. So distance, if you remember, the distance between 2 points is really the square root of the run squared, so x2 minus x1. This is just based on Pythagorean theorem. The run squared plus the rise squared, y2 minus y1, all squared. So if I look at my 2 points here, I could come up with a little formula here based on that x. We're going to have the square root of x take away 0, so I'm just using these x coordinates, x take away 0, which would just be x squared, plus, and then we have the difference in the y coordinates. So we're going to have 1/3 x squared minus 5 take away -1 squared. Okay, so that's our grade 10 formula for the distance between 2 points, which was built off of Pythagorean theorem. What we can simplify this to now is, let's see what we can work through here. So we've got our x squared, and then we have plus 1/3 x squared. So that's going to be 4/3 x squared. And then we've got minus 5, whoops, no, I forgot we have to square that. Minus 5 plus 1 would be minus 4, and that has to get squared. And then that's all square rooted, so I'm going to make that an exponent 1/2, because then I can use my chain rule with that. Let's see if we can tidy this up. Well, we could expand and simplify that, or we could just do the derivative from here. Why not? Let's just do the derivative. So we want to minimize the distance, right? So minimize means we want to find the critical number. We want to find that we're solving for the value of x. That would be a critical number, the possible max or min point for this function. Okay, so we want to minimize the distance, meaning we need to find values of x that will make this distance formula have its smallest value. So let's take the derivative then of that function, which I may not have enough room to write it on one line. I'm going to have to extend it probably to a couple of lines here, but chain rule is going to apply. I'm going to take 1/2 times whatever in the bracket reduce the exponent by 1, and then multiply by the derivative of what's inside. So this is what I'm writing below. We'll just multiply, like it'll go right beside here, but multiply. So the derivative of what's inside, the derivative of x squared would be 2x, and then plus, we're going to take the derivative of this, which also requires the chain rule. So we're going to have a 2, and then times 1/3 x squared minus 4, reduce that by an exponent of 1, or 1 power, so 2 take away 1, it would just be a 1 on that, times the derivative of what's inside that. So that's going to be 1/3 times 2 would be 2/3 x, and I believe that's the derivative of what's inside. So now we need to tidy this up so that we can begin to solve this for our critical number. I'm going to have I'm going to move some things down to the denominator, so I'm not going to take up so much room. This 2 is going to be on the bottom, as well as this entire thing to now the exponent positive 1/2 when it slides down to the bottom. This part's going to stay on the top for now until we tidy it up. So we're going to have a 2x on the top plus, and I'm going to go 2/3 x squared as I multiply the 2 through the bracket, minus 8. but that also has to get multiplied by 2/3 x. And then that has a denominator of 2, and then the x squared plus 1/3 x squared minus 4 all squared to the 1/2. And so on here. So we're going to have a 2x plus 4/9 x cubed minus, and then 16/3. Ooh, that's not pretty because I have fractions in a fraction, which, yuck. But that's okay, we'll deal with that. And there we are with that one. Now, let's see what we need to do with that. We know to get the critical numbers, we're going to set that equal to 0, and then we're going to solve this. So in the end, that denominator, I'm going to multiply both sides by that denominator to eliminate it, and that's going to leave us with, I think I can just continue writing below here. We're going to end up with this little equation that we have to solve. 0 equaling 2x plus 16/3, or sorry, minus 16/3 x, and plus 4/9 x cubed. Okay, I can put that 16/3 x with the 2x. Or I could multiply everything by the common denominator, which would be a 9. I think I want to do that first, and then I don't have to worry about getting common denominators to add my fractions together. So let's multiply everything by 9 here. 9 times 2 would be 18x. Plus 4x cubed minus, and then 16 times 9 divided by 3 would be the same as just 16 times 3, which is 48x. So I'm going to have my 4x cubed. That's 48x. That's going to be minus. Take away 10 off that. 38. Take off 8 would be minus 30x. And now I can common factor a 2x out of that. Oops. 2x out of that and get 2x squared minus 15. And then solving for my critical numbers, I'm going to get x equals 0, and out of this 2x squared equals 15. Divide both sides by 2, x squared equals 15 halves. X is going to be equal to positive or negative 15 halves. Sorry, square root of 15 halves. All right. From there, we just need to make sure we have our minimum happening. All right, so what I've done here is I've calculated the value of the function at each of those critical numbers. So f at 0 is equal to -5. We've got f at the square root of 7.5 being equal to -2.5, and likewise f at square root of 7.5 is -2.5. Now I already calculated the distance here. Both of these points here are on the y-axis, and the difference between -5 and -1 is 4 units. You could use the distance formula on those, but I mean that's just common sense as well. Now, I'm also going to find the distance, since these two values really are the same here. They're both ending up being a y-coordinate of -2.5. We're going to calculate our distance formula using that. All right, so I'm finding the distance between these 2 points, my point that I was given and the point where I found the critical number here. Put it into my distance formula, and I got a distance of 3.12. If I use the exact same point except with the negative square root 7.5 comma -2.5, I'm also going to get a distance of 3.2. So there are 2 points on the curve that would minimize the distance between points on the curve and the 0 point, comma -1. So I'll write my therefore statement and we'll be done. So I've written my therefore statement, and we have our minimum, our points at which we do have that, the points that are the closest to the 0, -1 point.